Hello, my name is Bram de Jonge. I am from the University of Groningen and I will talk about condition-based maintenance optimization based on matrix algebra. If we talk about condition-based maintenance, we talk about deterioration processes, and the most detailed deterioration processes are continuous time and with a continuum of states. This figure shows a sample path of a gamma process with a fixed level L at which failure occurs. Then, if we would like to use matrix algebra, we need to discretize the deterioration process. So what we do is we discretize time by making time steps of length delta t, and we subdivide the deterioration levels before failure into subintervals. We could then use, for instance, the discretization approach described in this study, and if we do that, then we get a Markov chain with a certain number of deterioration states m before failure and a failed state that we call state m plus 1. Transition matrix of such a Markov chain looks like this. Here we only have 5 states, but we could easily choose much more states to get a much better approximation. Then the maintenance setting that we are going to consider, it's quite a simple setting. We have corrective maintenance at cost CCM. We have preventive maintenance at cost CPM. We assume that maintenance durations are negligible, and we also assume that maintenance is perfect. We assume continuous monitoring of the deterioration level, and then we also assume that we don't have a planning time, so maintenance can be carried out immediately when we want to. The decision variable is the preventive maintenance threshold capital M. We carry out preventive maintenance when that level is reached or exceeded. Then the analysis. Our Markov chain for deterioration is absorbing. State m plus 1, the failed state, is the absorbing state. All other states are transient states. And the matrix P can be written like this. So Q is basically the same, but then without the row and column of the absorbing state. And R is the vector with failure probabilities. The matrix Q to the power k is important. That gives us probabilities of moving from one state to another state in exactly k steps. And if we sum all those matrices Q to the power k, we get the so-called fundamental matrix capital R. That can also be written like this. And for our analysis, the first row of this matrix is important. Entry j of this row equals the probability that starting from state 1, we are in state j after 1 period, plus the probability that we are there after 2 periods, plus the probability that we are there after 3 periods, and so on. That means that entry j of this first row equals the expected number of periods that we are in state j before being absorbed. And if we then take the sum of the first row, we have the mean time to failure. Then for the evaluation of preventive maintenance, it's important to realize that each maintenance action is a renewal point. And we can therefore use renewal theory to calculate the long-run cost rate given a preventive maintenance threshold. That cost rate is then equal to the mean cost per cycle divided by the mean cycle length. We have that deterioration is non-decreasing, and that means that entry j of the first row of R is also the expected number of periods that we are in state j before maintenance is carried out. So the mean cycle length is therefore equal to the first m minus 1 entries of the first row of R. So that's the mean cycle length. Each time that we are in a state, there is a probability of failure small r j, and that gives us then the mean cost per cycle. So we have here the probability of failure that is multiplied by CCM, and 1 minus that probability is the probability that we don't have failure, and that is multiplied by the preventive maintenance cost. Another way of writing this down is that we could also say that we always pay the preventive maintenance cost and that we pay the difference between the two if failure occurs. So this is the mean cost per cycle. Then the cost rate is then the fraction of the two, and that could easily be optimized. In an earlier study we have analyzed the exact same setting, but then by using simulation. And what you see here is the outcome for a specific problem instance. However, it takes of course quite some computation time to get such a smooth curve. That's because the simulation has to be carried out for many values of capital M, and each time the simulation horizon should be sufficiently long. If we use our matrix algebra approach with 100 states, then this is what we get. So the figure is virtually the same, but it only takes a fraction of a second to make it, so to do the computations. The reason for using simulation in that earlier study was that we also wanted to investigate the effect of other factors, namely a planning time, but also the effect of imperfect condition monitoring and of a random failure level. And we would now like to know how matrix algebra can be used if a planning time is added to our model. When preventive maintenance is planned, that basically means that we then do preventive maintenance action after a fixed planning time S. Then there's one complicating factor, and that is that failure can happen during the planning time. And because of that, we are going to distinguish two versions of the model. In the first version, we assume that we also need to wait until the end of the planning time for corrective maintenance. So that means that we have downtime, and during this downtime we then incur a downtime cost CD per unit of time that we are down. So that's CD. In the second version, we assume that an immediate emergency repair is carried out upon failure. And then we don't have downtime, but an emergency replacement is more expensive than a normal corrective maintenance action. So then the analysis for those two versions: we still have our transition matrix P, we also still have our fundamental matrix R, and then we are going to introduce a factor H, and for each M, the expected time until maintenance is planned is given as an element of this factor. In our initial model, this was the time until maintenance. We also introduce the factor Q, with for each M the probability of a sudden failure before preventive maintenance has been planned. So we have the probability of a transition from a state below M to the failed state, and this was the total probability of failure in our initial model. It's now the probability of a sudden failure. A complicating factor in this setting with the planning time is that the planning time can start in any deterioration state above M. We are going to use matrix V, in which entry Mj is the probability that the planning time starts in state J, given preventive maintenance threshold M. There is one special case: M is 1, capital M is 1, then maintenance will immediately be planned after the previous maintenance action, and the planning time always starts in state 1. For larger values of M, we can jump from any state below M to any state of at least M, and the other entries are all 0. There is a chance of a sudden failure without maintenance having been planned, and therefore the row sums of V are not 1, but if we add the factor with sudden failure probabilities, then we get the 1 factor. Another matrix that we are going to need is the matrix that we denote by capital S, and entry Ij here gives the expected number of times that we are in state J during the planning time, given that the planning time started in state I. This is the definition, and you see that it's very similar to that of the fundamental matrix. This is the only difference. We sum to S minus 1 because the planning time has finite length. And we can also write it like this without the summation sign. Now we have V times S, which is then also an important matrix, so the product of the two. What we do is we basically multiply probabilities of starting the planning time in a state by the corresponding expected number of periods that we are in a state. And that basically gives us the overall expected number of periods that we are in state J. So that's given by this matrix product. Each time that we are in a state, there is a certain probability of failure. So if we multiply V times S by R, we get the probability of failure during the planning time for each capital M, for each preventive maintenance threshold. And if we multiply Vs by the 1 factor, then we get the expected time that the unit is functioning during the planning time. And based on this, we can now provide expressions for the cost rate. So let's start with the policy with corrective maintenance at the end of the planning time. The mean cycle length is easiest. It's just the expected time until maintenance plus the planning time. So that's this. Then the mean cost per cycle. We can say that we always pay the preventive maintenance cost plus the difference between the two costs multiplied by the probability of failure. And that can be a sudden failure, but it can also be a failure during the planning time. And then we also add the downtime cost. So it's the expected time that the unit is functioning during the planning time, and then S minus that is the expected downtime. The cost rate will be the ratio of the two, the fraction, and this can then be optimized. For the case with emergency repairs, the cost per cycle is the same. Only difference is that we then don't have the downtime cost, so this part cancels out. That's the good news. But we then also have that the mean cycle length also goes down, because we are only going to add parts of the planning time over here. So that part will be smaller than S. That means that this is then the expression for the mean cost per cycle. So indeed, same but then without downtime cost. And the expected cycle length is then equal to this, with here the expected time that the unit is functioning during the planning time, which is below S, smaller than S. The cost rate is again the ratio, and that can be optimized again. So then an example, a discretized gamma deterioration process with a planning time of 0.2. We will set the preventive maintenance cost to 1, the corrective maintenance cost to 3. And then if we set the downtime cost to 0 and the emergency repair cost equal to the corrective maintenance cost of 3, then the policy with planned corrective maintenance is always better. And it's just because cycles are longer, because we wait until the end of the planning time and we don't pay for that downtime. However, when the downtime cost is going to increase, at some point the policy with emergency repairs becomes better. And if then the emergency repair cost starts to increase, then the policy with planned corrective maintenance becomes better again. So what we basically see is that the ratio between the downtime cost and the emergency repair cost, that's important. If the downtime cost exceeds some threshold that depends on the emergency repair cost, then it's better to use emergency repairs. So that's what we see in this figure. Another instance then, and here we show the effect of the length of the planning time S. Longer planning time has a negative impact on both policies, because the condition information cannot be used during the longer planning time, and the impact is largest for the policy with planned corrective maintenance, because in that case we have a risk of very long downtimes. We can also say that if the planning time exceeds some thresholds, then it's better to use the policy with emergency repairs. And here we also see the effect on the optimal preventive maintenance threshold, capital M. Longer planning time indeed means that we initiate maintenance earlier, and the effect is again strongest in the case with planned corrective maintenance. And then finally here the effects of the amount of volatility in the deterioration process. If the volatility increases, everything becomes less predictable and the cost rates of both policies go up. Either of the two can be better. So here we see an example where emergency repairs are better. But here is another example, and there you see that corrective maintenance, planned corrective maintenance is better. So what we can say is that if one of the two policies is better, then it's still the case for a different behavior of the deterioration process. So when choosing which policy to use, the exact deterioration process is not that important. Then I would like to finish with some suggestions for future extensions. If the planning time is mainly needed for ordering spare parts, a second decision could be added to the model. And that is then when a spare part arrives, we could replace the unit immediately, but we could also wait for some time if the unit is still in reasonable condition. We could also consider imperfect maintenance, so that we do not always go back to the as good as new state after maintenance. And we could also consider condition monitoring that is not perfect, so that we don't know for sure in which deterioration state we are. And then finally, a combination of planned corrective maintenance and emergency repairs could be considered. So if failure occurs early during the planning time, an emergency repair may be better, whereas we could maybe wait for the planned maintenance intervention when there is not that much time left. And that's basically it. So thank you for watching.